Hello and welcome to the 11th session of this TA course. The course name is Advanced Thermodynamics and Statistical Mechanics. I am Umar Rashid and I am working as a PhD student in Indian Institute of Science, Bangalore. So I held a TA session every week on Fridays, in which I will try or I will show you how to solve the different questions from the previous years or even this year. And in the meanwhile, while solving those questions, I will repeat some of the basic concepts about this course, and these concepts allow you to solve the questions and that have been given in the past, and also to solve the questions that are present in the that will be given during the course during the time period of this course. Okay, so today is the 11th session, and I'll briefly tell you about what we have discussed so far. So till now we have discussed, nowadays we are discussing more about statistical mechanics, or we call it as a statistical thermodynamics. So till now what I have discussed is so till now what I have discussed is the what is statistical mechanics, and I have told you about the probability, then various types of distributions, then what is a distribution function. Okay, then I have given concept about bosons, I have given about fermions. Okay, or we can also give boltzons. Okay, then I have given the concept about permutations and combinations. In this I have discussed how we can also distribute energy of different particles. Okay, so this is the one I have, and in the last session we have also solved some of the questions. These questions were regarding mostly about partition function. Okay, so today we'll be dealing more about the partition function. This is very important, a central core identity in statistical thermodynamics. Just like we have what we call this wave function in statistical mechanics, similarly we have partition function in statistical thermodynamics. It contains the information about your system, and from this partition function we can calculate the different thermodynamical parameters of the system. Okay, so this is the partition function. Okay, now we'll be dealing with today I will show you how to calculate the partition function for different molecules, and how we can distribute the partition function among different degrees of the freedom, like translational, vibrational partition function, similarly rotational partition function, and the electronic partition function. And at the end then we'll solve some of the questions. Okay, so before going to the partition function, I'll tell you briefly about one of the most important approximation in statistical thermodynamics, that is called as Stirling's approximation. Now if you see, in case of statistical thermodynamics, we have to calculate the various integrals, or we have to calculate various numbers, various factorials like n factorial. Okay, so for example, if the n is very very small, then we can easily calculate it. Okay, now it's not we can use normal methods, but once the n goes very very high, that means number of the distributions or number of the particles that we are concerned with, it goes very very high, then what happens is that calculating n factorial is a problematic. Okay, it's a mathematical challenge. So what we do is we use an approximation called as Stirling's approximation. So that's Stirling's approximation. Okay, so Stirling's approximation is the approximation that is used to calculate n. Now you should be sure, you should keep in the mind that Stirling's approximation is only possible, it's only valid when the n is very very high. If the n is very very low, then the Stirling approximation does not hold true. Okay, so let us go tell you more about the Stirling's approximation. Now, as I have written here, once we evaluate distribution functions in case of the statistics, we have to often factorize some of to calculate some of the factorials of very high numbers, just like in case of binomial distribution. For example, this is the function that I have shown here, that is a binomial distribution. Okay, f of b x is n factorial p raised to power n 1 minus p n factorial n minus x divided by x factorial into n minus 1 factorial. Now if you see here, we have to calculate different factorials. One is n factorial, second is x factorial, then we have n minus x factorial. Okay, so 3 factorials we have to calculate. Now in order to calculate those factorials, we use something called as the Stirling's approximation. Now Stirling's approximation is given by this parameter. Okay, that means n factorial is equivalent to n raised to the power n e raised to the power minus n raised to 2 pi n. So from this we can calculate Stirling's approximation. Now if we take this Stirling's approximation in the simple method, I can write. So I will write here Stirling approximation. Okay, so I have shown there that it is n factorial is given by n raised to the power n e raised to power e raised power minus n under root 2 pi. Okay, now what we'll do is we'll just take a, I will show you one of the simpler form of this. Okay, so what we'll do is we'll take a log of this. Okay, so we'll get ln of n factorial is given by ln of n raised power n plus ln of e raised power minus n. Okay, so what we'll get is ln of n factorial will be given by, this will be n ln of n, okay, minus n. Okay, so this is the little simplest form of Stirling's approximation. Okay, n ln of n factorial is equivalent to that of the n ln of n minus n. Okay, so this is the simplest form of Stirling's approximation. Okay, now Now but if we can add also a correction factor, that is under root of 2 pi n, to make it more accurate. Okay, then there is also a slightly more accurate form of the Stirling's approximation, that is n factorial is n raised power n e raised power minus n under root of 2 pi n 1 plus 1 by 12 n. Okay, this is the correction factor that is introduced, but in most of the cases the difference is very small. The additional term, it gives a way to access whether the approximation has a larger error. Okay, now Stirling approximation is very useful for approximating the log of factorials. Okay, so which find its application in evolving the entropy in terms of multiplicity, as in Einstein. So if we try to solve the Einstein's equation for the solids, then log of n is n log of n. That's what I have actually already shown you. Natural log of n factorial is equivalent to n ln of n minus n plus ln of under root 2 pi n. Okay, but the last term may be neglected, so that the working approximation is this. So this is the this Stirling approximation is very important for statistical mechanics. Okay, now Schrodinger, he also gave he calculated the different this n factorials, and see how this approximation is accurate. Now if you see that n is 1, okay, so if we calculate n factorial, it is given by 1, but if we use the Stirling's approximation, we will get 0.922. Okay, so how much our error will be? Error will be 7.7%. okay, now in a stat, if we use the natural log, so ln of natural log will be 0, but ln of this will be -1, so the error we cannot calculate. But if we take n as 10 and we calculate n factorial, it is given by this, and using the Stirling's approximation, it is given by this. So the percentage of the error decreases very high, so 0.88. okay, but if we use the natural log, then the error is little bit higher. Okay, but if we still increase the n, so we will get very close to that of the original value of the n factorial. Now this is only n is equal to 100. If we go on increasing more and more the value of this n, then the Stirling's approximation, the error is very marginal, so that time we can use it perfectly. Okay, now there is another form of an integral called as a zeta function, everything that I want to tell you about. Okay, so for example, this is a form of an integral that is happening in statistical mechanics. So you see the integral from 0 to infinite is x raised power n e raised power x plus minus 1 into d of x. The evaluation of this class of an integral can be done in terms of two special functions. One is called as a gamma function and another is called as Riemann zeta function. Okay, for example, if we use a gamma function, then the value of this, if it is -1, it is given by gamma n minus 1 zeta n plus 1. Okay, and if it is plus, then we have 1 minus 1 by 2 raised power n gamma n plus 1 zeta n plus 1. So whereas zeta is the Riemann zeta factor and gamma is a gamma function. So this integral is very important in statistical mechanics. Now as I have shown you here, the gamma function. So what is the gamma function? Gamma function, which is given by this gamma n plus 1, it is given here. Gamma n plus 1 is 0 to infinite x raised power n e raised power minus x into d of n, but it can be related to another integral, that is n factorial 0 to n x raised power n e raised power minus x into d of n. So this value, you see this and this, it is almost equal, right? So zeta is actually, zeta n plus 1 is actually equivalent to that of a n factorial. Okay, and zeta n plus 1 is n zeta. So if we have zeta n plus 1, then it is n zeta n, but zeta n plus 1 is yes. So this is like sort of we can say that zeta n is given by zeta n plus 1 divided by n. Okay, so this is the gamma function, we call it as a gamma function. Other important concepts about the gamma function is, if we see that gamma function of 1, it will be 0 factorial, it is always equivalent to 1. Similarly, d minus by 2 minus 1 is equivalent to gamma d by 2, right? Because we are subtracting 1 from it. Similarly, gamma multiplied by gamma 1 minus n will be equivalent to pi divided by sine n pi. So this gamma function is mostly used in order to evaluate various statistical integrals. Now you have to take care. Now another that I showed you is Riemann zeta function. Okay, so the zeta function is given by that I have shown here, right? This evaluation of this indicator zeta n plus 1. So it will be given by zeta n is equal to 1 plus 1 by 2 raised power n plus 1 by 3 raised power n, which can be given by summation over k from 1 to infinite k, and where k is an integer. Okay, so this is zeta function. So these two functions are mostly used in statistical mechanics for the evaluation. Now we have okay, previously I have shown you that there are different types of the molecules. Okay, where we are and different types of the distributions apply. Okay, different types of statistical mechanics apply to those. Yeah, so everything depends upon what is the spin of the different systems. Okay, so based on the spin, different particles have been classified. Okay, so one of the, as I have written here, the most important classification of the particles is on the basis of their spin, or also called as intrinsic angular momentum, because spin is responsible for the intrinsic angular momentum in case of quantum particles. Okay, we say that those particles which have a half integer spin, half integer spin means 1 by 2, 3 by 2, 5 by 2. Okay, so this is a half integer spin. Those are called as fermions. Okay, they, on those fermions there is a special principle called as a Pauli's exclusion principle, where the integer spins are called as bosons. Okay, and on this we apply Bose-Einstein statistics. Okay, so we have fermions on which Pauli's exclusion principle applies, whereas on bosons Pauli's exclusion principle does not apply. If so, if we say that in case of the fermions, you might have seen in quantum mechanics that we apply something called as an asymmetrical wave function, whereas for bosons it should be symmetrical wave function. So similarly in statistical mechanics we will have different function for statistics for bosons and different for fermions. Okay, the electron, for example, it's actually a fermion. Okay, because it has a spin of 1. If we say quark, it's also a fermion, it has a spin of 1 by 2. Similar, but if we say a photon, the photon has a spin of 1, so it is a boson. Okay, if we say graviton is also a boson, it has a spin of 2, and Higgs boson, it has a spin of 0. So we have photon as a boson, we have graviton as a boson, and we have Higgs boson as a boson. The spin classification of the particles, it determines the nature of energy distribution. So as I told you, because of that spin there is a different energy distribution of different particles. Okay, those particles which are having the integral spin, that means which are bosons, they obey Bose-Einstein statistics, whereas those who have an integer, they apply Fermi-Dirac statistics. Okay, now as I have written here, Carroll describes fermions and bosons as follows. Particles come in two types. The particles that make up matter are known as fermions. So fermions are the particles that make up matter, and the particles that carry force, they are called as bosons. So if there is something that make up the matter, they are fermions, like electron, proton. But the particles who carry the forces, they are called as boson, like Higgs boson, light, because they don't have any mass, but what they have is they have some energy. Okay, the difference between the two is that fermions take up space, whereas bosons can pile on top of one another. Okay, so this is the most important thing. Fermions, if you take a one fermion with one spin, you cannot take another fermion nearby, because the Pauli's exclusion principle applies. Okay, but in case of bosons, it's not the case. They can pile over one another. You can't just take a pile of identical fermions and put them all at the same place. The law of quantum mechanics would allow it. The fact that the two identical fermions cannot occupy the same state is further described by the Pauli's exclusion principle, and the fact that bosons is further described as Bose-Einstein condensate. Okay, so we have two types of particles that we have, fermions and bosons. 1 minute. Now this is the main difference between fermions and bosons. Fermions take space, so there cannot be two identical fermions at the same place at the space, but bosons can collapse. That's like you have a lot of photons at one place. The fermions can occupy space. Okay, and those are described by the Pauli's exclusion principle, whereas the bosons are described by the Bose-Einstein condensation. Okay, so more about fermions. Okay, in fermions are the particles, as I showed you before, which have an half integral spin, and they are therefore constrained by Pauli's exclusion principle. That means two set of fermions or electrons cannot have the same set of four quantum numbers, right? So particles with integer spin are fermions. Okay, fermions include electrons, protons, as well as neutrons. Okay, these are the particles that make up the matter. The wave function, which describes a collection of fermions, must be anti-symmetric with respect to exchange of identical particles, whereas the wave function for a collection of bosons is symmetrical. So what it means is that if we have two particles, electron 1 and electron 2, okay, so as I'll show you. So we are talking about fermions. Okay, fermions should have a symmetric wave function. Okay, asymmetric. What it means is that if we have a electron 1 and we have electron 2, okay, so if we have a wave function for an electron 1, that is psi 1, okay, and then we have another wave function psi 2, okay, then what we want is that once we exchange the, for example, this psi 1 is at x1, this is at x1, and this is at x2. Okay, we have to create a wave function in such a way that uh, when we exchange these two, they should be antisymmetric. For example, if the wave function of 1 is psi 1, okay, it is present at x1, then for wave function for this is psi 2, it is present at x2. Now this is symmetric with respect to this, so I will call this as a psi. Okay, now psi a, but there can be another possibility, right? So psi b, where these two are, because these are indistinguishable, right? Psi 1 is at x2 place and psi 2 is at x1 place. Okay, in order to create an anti symmetric wave function, we use something called as Slater determinant. Okay, so how Slater determinant works is psi 1 x1, psi 2 x2, then here is psi 2 x1, this is psi 1 x2. Okay, this will be psi antisymmetric. So if we solve this, what we'll get is we'll get a combination of above two. Okay, so for sorry, if we are creating a determinant, then what we have to do is okay, so what we have to do is we have to take either one column or one column or one row for a particular. So we have taken columns as wave function. Now this should be same, this will be x1, this will be x1, this should be x2, this should be x2. So x2 minus psi 2 x1, psi 1 x2. Okay, so this is psi anti-symmetric. Okay, but now what we are doing is we are thinking that now what we do is we'll exchange E1 from x1 to x2 and e2 from x2 to x1, right? So once we exchange, what we have to do is we'll write a wave function psi of nt star. What we'll write is, now the position is changed, so psi1 x2, psi2 is present now at x1. What I'm doing, I'm changing the position from x2 to x1. Similarly, psi2 is present at x2 and psi1 is present at x1. Okay, now if we compare psi of nt and psi star of nt, what we'll get? Psi of nt is actually equivalent to negative of psi of star of nt. So this is called as uh, an anti-symmetric wave function. Okay, this is called as anti-symmetric wave function for fermions. But if we take that for bosons, psi of nt should be equivalent to psi of nt star. Okay, so this is for bosons. So this is symmetric and this is symmetric wave function. Okay, so this is the case for you. Now the fact that electrons are fermions is foundational to the building of a periodic table. Now if you see that because the electrons are fermions, that is the reason we have different shells, right, different orbitals. Okay, otherwise if electrons are bosons, then we'll club every proton or every electron into a same level because they can occupy. But since they cannot occupy, so they create something called as a Pauli's pressure. As a result, we have to use the higher levels. Because of those levels, we have different atoms with different chemical and physical properties, and they give rise to the periodical table. Okay, now if you also see that this fermionic nature of electrons, they also govern the behavior of electrons in a metal at very low temperatures, where all the low energy states are filled up to some state called as a Fermi state. If we see in case of a metal, and we say something called as a Fermi level, the Fermi level of the metal is the level up to which all the levels are occupied at 0 Kelvin, because that time we don't have any excitation, right? So if we and these are described by the Fermi-Dirac statistics. So if we have, just like I'll show here, I have shown you previously what is the Fermi-Dirac distribution. I think it is f of E is given by 1 divided by e raised to the power minus e by kt plus 1. Yeah, I think that is the Fermi-Dirac distribution. Just a second. Okay, so it is now if we write the Fermi-Dirac distribution, okay, so it is E minus EF by kt. So this is the Fermi-Dirac distribution. Okay, it tells us that what is the probability that a particular level is occupied at one time. Okay, so if we want to plot it, okay, at t at 0 Kelvin, we want to plot the Fermi-Dirac distribution. So I am plotting Fermi-Dirac distribution here. Okay, this is f of E. Okay, now we have to be very, now this is very important. Okay, now at t is equal to 0, that means That means when t is equivalent to 0, e raised to the power e minus ef by kt. Since t is 0, so this will be infinite. Now this is here. Now at t is equal to 0, we have this function. Okay, for E which is less than EF. Now those energy states in which E is less than EF, like this state, what we'll get is E minus EF by KT. Since this is 0, it will be infinite. Since this is 0, this thing is 0, so anything raised with power 0 is okay. So we'll write here T E minus EF by 0. Okay, now since this is 0, it will be exponential 0, exponential infinite, sorry, that will be equivalent to 0. So f e will be equivalent to 1, so we'll write 1. Okay, up to the energy state where we'll write it in terms of e minus ef. This is given by 0. Okay, so this will be 1, this will be 0. You got the point? Now when this is case first, case second, for e greater than ef, once e is greater than ef, what we can do is what we'll do is we can neglect 1. Okay, so we have and this is minus exponential. Okay, for e greater than ef, what we'll have is we have e raised power e minus ef by 0. Okay, but since it is positive, it will be e raised power infinite plus 1, so f of e will be equivalent to 0. Okay, this thing is at, this is the Fermi Dirac distribution at 0 Kelvin. Okay, okay, this function is at 0 Kelvin. Now what will happen is that once we go on increasing the temperature, okay, so once we go on increasing higher temperatures, for example at T greater than 0 Kelvin, then what will happen is that those states which are very near to the Fermi energy, this energy, so here is Fermi level, those states which are very near to the Fermi level, they will empty and they will go to the higher states. What we'll get is we'll get if this is 0, this is e minus ef, this is f of e, what we'll have is okay, if we go on increasing the temperature further, Okay, so if we call this as, this is T1, this is T2, this is T3, we should know that T1 is great less than T2 is less than T3. Okay, so this is the how the Fermi energy distribution changes as a function of temperature. But uh, because of the half integral spin of the fermions, whereas bosons there is no such thing. Okay, okay, so this is determined, I told you, this is called as Fermi Dirac statistics. Now another aspect of nature of fermions is was determined by Carroll. Okay, what Carroll said is that ordinary matter, it includes elements of the periodic table. They are just made of three fermions: electrons and up and down quarks. Okay, they are responsible for the great difference in scale between the nucleus and an atom. Quantum mechanically, an electron can be considered to be a wave packet that obtains its relative mass by interacting with Higgs field. A small mass energy translates to a relatively long characteristic wavelength, so the particle is spread out in the space. This gives a relative larger size to the atom as a whole. So uh, since we know that what Carroll said is that the particle matter is made of periodic elements. These elements are made of electrons and up and down quarks. These are responsible for very large difference of scale in between the nucleus and atom. An electron is actually a wave packet. It obtains its mass by interacting with the Higgs field. Because of the smaller mass, it gets translated into a very long characteristic wave packet, and this spreads in the space. This gives relatively larger size of an atom as a whole. The up and down quarks, which make up the protons and neutrons, okay, in the nucleus, have relatively much larger mass for a strong interaction. So they have very higher mass for a strong with the Higgs field. The characteristics wavelength of their quantum mechanical wave packet is smaller. Thus, they have a smaller wave packet. They make up the nucleus as an entity which is much smaller than that of an atom. The approach to the scale of nucleus and atom should be compared to the description of particle confinement and the Heisenberg's uncertainty principle. So because of the what Carroll says is that because of the difference in because of the mass of electrons is very low, as a result, once it interacts with Higgs field, it gets spread out. But once the quarks, which make up the nucleus, they interact, they have very high mass. As a result, they are very much confined. That's the reason nucleus is of the order of 10 to the power minus 15 meters, whereas atom is of the order of 10 to the power minus 10. Okay, so now there is this quarks. So quark is actually a elementary particle and is a fundamental constituent of the matter. Okay, they combine together to form particles called as hadrons. The most stable of the hadrons are protons and neutrons. Okay, so they make up the atomic nucleus. Okay, so the quarks are actually the constituent elements for hadrons, which are like proton and neutrons are the hadrons. So all the observable matter is either made up of quarks, that is up and down quarks, like and or it is made up of the electronics. Now because of something called as a color confinement, okay, the quarks cannot be found in isolation. They are only found within hadrons. So for example, which include baryons, so like protons and neutrons and mesons, like quark gluon plasmas. For this reason, of which is known about the quarks has been turned from the hadrons. Okay, so this is, for example, if we take a like a proton, it is made up of two up quarks and one down quark, and a gluon that mediate the force, or they bind them together. Okay, So this is the corpus. So the difference between corpus made up of the nucleus, whereas electrons made up the rest of the space. So all these three together, they constitute the matter. Now we have also something called as bosons. As I told you before, that bosons are those fundamental particles which have spin that is an integer spin, like 1, 2. So for example, light, it's a boson. Okay, so bosons are particles which have an integer spin and are therefore not considered under Pauli's exclusion principle. Okay, therefore their energy distribution is considered by another distribution called as a Bose-Einstein statistics. Okay, and that's like Bose-Einstein is given by 1 divided by e raised power minus e minus ef by no sorry minus 1. So this is Bose-Einstein statistics. Okay, so the wave function of these bosons, for a wave function of two bosons, should be symmetric with respect to exchange of any two identical bosons, whereas the wave function of fermions is antisymmetric. At very low temperatures, the bosons can behave very differently than fermions because an unlimited number of them can collect in the same energy state. Now, in case of the fermions, once it's a low state, all cannot occupy the same space because of Pauli's exclusion principle. But it is not the case in case of bosons. All the bosons can be present at the same energy level, thus they behave like different thing. Okay, this the collection into a single state is called as condensation. So you at 0 Kelvin for lower temperatures, all the bosons will set in a single state. So this is called as a condensed state or Bose-Einstein condensation. Okay, this condensation is actually responsible for superfluidity in case of liquid helium. Okay, coupled particles can also act effectively as bosons. So for example, coupled particles have been seen in, just like in case of BCS theory in superconductivity, where we have Cooper pair theory, right? The Cooper pair of electrons, they act as a bosons and condensate in a state which demonstrates zero electrical resistance. Okay, so it is because of these bosons that we see superconductivity in, because the two electrons interact among themselves to form the boson. Okay, bosons also include photons, and the characterization of photons as particles with frequency dependent energy is given by Planck's relationship allowed Planck to apply Bose-Einstein statistics to explain thermal radiation from a hot cavity. Now, because of that Bose-Einstein statistics, the Planck's we see that the behavior of a black body radiation is explained by the Planck's radiation law. This Planck's radiation law, he applied the Bose-Einstein statistics, and once he applied, then he was able to explain the thermal radiation that's coming from a black body at very higher as well as lower temperatures and at very higher as well as wavelengths. That was not possible before, while considering only the quantum mechanical laws. Now if we see that these bosons, they are the fundamental particles which carry force. Okay, like the photon, it carries the electromagnetic force. The bosons do not take up the space, so bosons will not take up the space and they constitute solid objects, or they cannot constitute a solid object, but they can condensate in the same location in space. Okay, vector boson with spin 1 are the gauge bosons from standard model. Now if we see gamma, the photon for an electromagnetic wave force, G is the eighth type of gluon which participate in strong interactions, Z is the neutral boson in the weak interaction, W plus and Wy are the charged bosons for weak interaction. The scalar boson H0 is called as a Higgs boson which has a spin of 0. The proposed tensor boson G, called as a gravitron with spin 0, is for the gravity. So all these things, they have a they have a full integral spin, like means they have an integral spin, either 0, either 1, or either 2. Okay, now we'll talk a little bit about the Bose-Einstein condensate. Okay, so what is Bose-Einstein condensate? In 1924, the Einstein pointed out that bosons could condensate in an unlimited number into a single ground state. Okay, since they are governed by the Bose-Einstein statistics and are not constrained by the Pauli's exclusion principle. Little notice was taken into curious possibility until the anomalous behavior of liquid helium at low temperature was carefully observed. Okay, so when the helium is cooled at a critical temperature, that means at 0.17, a remarkable discontinuity in the heat capacity occurs. So we have a heat capacity, that means the energy that is required to change the temperature of a particular amount of substance through 1 degree. Okay, it's called heat capacity. But if we measure the heat capacity of helium, what happens is that there was a discontinuity at 1 2.1 K. Okay, now the liquid density drops and a fraction of liquid becomes a zero viscosity, called as a superfluid. So at 2.17, when helium is cold, what happens is that there is discontinuity in the heat capacity, density drops, and what happens is that the liquid becomes very highly fluid, called as a superfluid. Superfluidity arises from the friction of helium atoms which had condensed into the lowest possible energy states. So this superfluidity, only a fraction has a zero viscosity. Okay, now the condensation effect is also credited with producing superconductivity. Now this condensation effect has also been shown to produce superconductivity. For example, if we see in case of BCS theory in superconductors, where where they proposed that a pair of electrons, they are coupled together by the latest interactions, and these pairs are called as a Cooper pairs. They act as a bosons, and because of that bosons, they can go into a state of zero electrical resistance, which gives the superconductivity. The condition for achieving a Bose-Einstein condensed state are quite extreme. The participating particles must be considered to be identical. So for them, the particles must be considered identical. They cannot be they cannot be distinguishable. Okay, or unidentical, and this is the condition that is difficult to achieve for whole atoms. The condition of indistinguishability requires that the de Broglie wavelength of the particles overlap significantly. This requires extremely lower temperature so that the de Broglie wavelength will be long, but also requires a fairly high particle density to narrow the gap between the particles. So this is the conditions where we can achieve the Bose-Einstein condensate. We should have a very low temperature and very high density. Now what is the Bose-Einstein condensate? Is something that in which all the particles, they club together into the lowest energy states. As a result, their behavior changes. Okay, now that's not possible in case of the fermions, because the fermions they are subjected to the Pauli's exclusion principle. Now as I have shown here is that because since 1990 there has been a very search in the Bose-Einstein condensation, as it was discovered that Bose-Einstein condensate could be formed with ultra cold atoms. The use of laser cooling and the trapping of ultra cold atoms with magnetic traps had produced temperatures in the nanokelvin range. Cornell and Webmin, along with Kretel of MIT, received the 2001 Nobel Prize in Physics for the achievement of Bose-Einstein condensation in dilute gases of alkali atoms and for early fundamental studies of the properties of condensates. Cornell and Webmin lead an active group at the University of Colorado Boulder, which has produced Bose-Einstein condensate with rubidium atoms. Other groups at MIT, Harvard, and Rice are very active in this rapidly advancing field. So these are the type of the groups that are there. Now this image, as actually I've shown you, it was produced by GILA, University of Colorado Boulder. It is specifically credited to Mike Matthews of GILA research team. The GILA research team was able to image the BEC as it was cooled from 200 nanokelvin down to reported temperature of 20 nanokelvin. The coherent BEC emerged as a peak representing a group of atoms with the same velocity surrounded by a field of normal atoms with random velocity. The BEC is actually Bose-Einstein condensate, represented about 2000 atoms of rubidium. If you see here that we have this this is the image. Okay, these are the atoms, and this area they have very high they have velocity same atoms. So these consist of 2000 rubidium atoms as we go from higher to the lower temperatures. So these are called as a Bose-Einstein condensate. The Bose-Einstein condensate, they are made up of ultra cold dilute gases. Their observation marked the culminations of period of development of technique for achieving very low temperatures and the confinement of atoms at those temperatures. The use of laser cooling and the trapping of ultra cold atoms with laser trapping has reduced temperatures up to nanokelvin range. The JLA team reported that the laser cooling brought temperature down to 10 microkelvin. Some 10 million atoms were trapped by the laser cooling and held in a magnetic trap. They are held in a place by a quadruple magnetic field, but such a field has a hole in it that will allow atoms to escape. The JLA researchers devised a way to rotate the hole at a rate that the atoms could not follow, effectively sealing the hole. The last stage of the cooling involves evaporation of the more energetic atoms from the magnetic track, leaving behind the collection of atoms that are colder and more dense. So this is a way in which the Bose-Einstein can be formed. Now in statistical mechanics, there is something called as ensemble. Okay, so this is a very important uh, study, like what is an ensemble. Okay, so if we consider that an ensemble is actually also called as a statistical ensemble, it is actually a collection of large number of a system, identical system. Okay, if we collect a large number of an identical system, it constitutes an ensemble. Okay, they are as large as infinite, each of which represent a possible state that a real system might be. So for example, we have a system, we create an infinite number of copies of that system, and we say that each system, each of these states, these systems, these virtual copies, they will represent a state of a system in which our real system can be. In other words, a statistical ensemble, it consists of a set of system of particles used in statistical mechanics to describe a single system. The concept of an ensemble was introduced by Gibbs in 1922. Okay, now a thermodynamical ensemble is a specific variety of statistical ensemble that, among other particles, is in statistical equilibrium and is used to derive properties of thermodynamical system from the laws of classical or quantum mechanics. Okay, now why do we need to create ensemble? Okay, there are different types. Why do we need to create using the ensemble properties, we can determine the thermodynamical properties of the materials or matter. Okay, for example, what is a physical consideration? As I have written here, that an ensemble, it formalizes a notion that an experimental repeating an experiment again and again under same microscopic conditions but unable to control the microscopic details may expect to observe a large different outcomes. So if we have if a scientist is performing an experiment and it is performing at same microscopic conditions, same conditions of temperature, pressure and volume, but every time there will be a little different observation because he is not able to control the microscopic outcome. Okay, the notional size of ensemble in thermodynamics, statistical mechanics, and quantum statistical mechanics can be very large, including every possible microscopic state of a system could be in, consistent with the observing microscopic properties. For many important physical cases, it is possible to calculate average directly over the whole thermodynamical ensemble to obtain explicit formula for many thermodynamical quantities of interest, often in terms of appropriate partition functions. So the idea of the ensemble is that we represent an ensemble, a collection of states, right, and which possibly represent all the microstates that are present in a system, which are present at same microscopic system. So if we have an ensemble, it contains all the microscopic systems. If we take an average over an ensemble, so what we will determine is that average, we can determine the average thermodynamical properties of a system. Okay, now there is ensemble has to be at the average, or there is always called as statistical or a stationary ensembles. Now ensemble, since it contains all the systems, all the microstates that can be present at a particular thermodynamical states, it does not necessarily need to change. In fact, ensemble will not evolve if it contains all the past and future phase of a system. If our ensemble contains all the possibilities, then it does not need to change, because it already contains everything if a system is changed or it was before. So such an ensemble which does not change with the time is called as a stationary ensemble and is said to be in statistical equilibrium. Now, the word ensemble is used for a smaller set of possibilities sampled from a full set of possible states. For example, a collection of walkers in Markov chain Monte Carlo iteration is called an ensemble in some iteration. The term ensemble is often used in physics and physical infrastructure. In probability theory, the term probability space is more prevalent. Now there are different types of ensembles. Okay, we have a microcanonical ensemble, we have a canonical ensemble, we have a grand canonical ensemble, we have a gibbous or isobaric isothermal thermal ensemble, or an enthalpy or isoenthalpic isobaric ensemble. Now what are these different ensembles? They different that how these things interact. If we have a microcanonical system ensemble, the number of the particles, the number of the volume, as well as the energy remains constant. So as a result, it does not interact or does not lose energy to the outside system. This is a microcanonical ensemble. However, if we remove the insulation, we can create a canonical ensemble which has same number of particles, where and volume is constant, but the temperature is constant. Here the energy is not constant because it is able to interact with the outside surroundings. So then we have a grand canonical. In grand case of grand canonical ensemble, we'll have change in number of particles as well. As a result, the chemical potential will remain constant, volume will remain constant, and the temperature will remain constant. So this is grand canonical ensemble. So these different kinds of ensemble, they are used to determine different properties of the system, different systems, depending upon how it interacts with our surroundings. Then we have a gibbous, which have constant number, constant pressure, and constant temperature, where there is no constant volume. And then we have enthalpy, where we have constant number, constant pressure, and constant enthalpy. Okay, so these are called as different types of the canonical systems. Now we have almost finished this canonical grand canonical system. We'll go towards the partition function. Okay, so now we have a concept called as partition. As I told you before, the partition function is fundamental to the it is fundamental to the statistical mechanics. Okay, the partition function is, it describes that it describes the statistical properties of the system in a thermodynamical equilibrium. Okay, the partition functions, they are the function of thermodynamical state variables such as temperature and volume. Partition function is like a wave function in statistical mechanics. Using the partition function, we can determine different thermodynamical properties. Most of the aggregate thermodynamical variables of a system, such as total energy, free energy, entropy, and pressure, they can be expressed in terms of partition function or its derivatives. Partition function is a dimensionless quantity. Okay, now each partition function, it is constructed to represent a particular statistical ensemble. Okay, so for example, which in turn corresponds to a particular free energy. The most common statistical ensemble is have named partition functions. The canonical partition function applies to the canonical ensemble in which the system is allowed to exchange heat with the surrounding at a fixed temperature, volume, and the number of particles. Then we have a grand canonical ensemble. It applies to the grand canonical ensemble in which the system can exchange both heat as well as number of particles with the surroundings at fixed temperature, volume, and chemical potential. Other types of the partition functions, they can be identified under different circumstances. Okay, so the partition function has both meaning as well as it has significance. So what is a partition function? Okay, so we'll determine what is a canonical partition function. For example, if we assume a thermodynamically larger system which is in thermal contact with the surrounding, so for example we have a system like here, and it is able to radiate heat, okay, in all the sides. The temperature outside and inside is then T. Now volume and the number of the particles are constant. A collection of this kind of system comprises an ensemble called as a canonical ensemble. Now if we repeat this by infinite times, this system by infinite times, we call this as canonical partition function, canonical ensemble. Okay, so now what is the physical significance of partition function? Okay, so partition function is is, I will write here, partition function of a system, for example Q, it provides the tools to calculate the probability of a system occupying state I. So what is a partition function? Partition function, it tells us about what is the probability that a system is occupying the state I. Okay, so that is partition function. Now it depends on composition of the system, it depends on volume, and similarly number of particles. Okay, now we can say that larger partition function means more accessible energy status at temperature T. Okay, so larger the partition function, more energy states are accessible. The smaller the partition function, less energy states are accessible. So partition function, as I told you, it tells us the probability that a particular state I is occupied at a temperature. Now we have what is the general form of partition function? So if we write Q is equivalent to summation over all the states I exponential minus EI by KBT. So this is the general form of partition function. Okay, this is general form of partition function. Now if we consider now we have seen here that the sum is over all the states of a system, so that means that it requires that energy levels of the entire system, it must be known, and the calculation has to be calculated over all the states of a system. Okay, this limits the type of the systems that we can derive properties for. For example, if we consider for ideal gases, we assume that energy status of molecules are independent of those in other molecules. Now, in case of the ideal gases, since the gases don't interact with one another, that means the energy state of one gas are different from that of energy states of another system. Okay, thus that means the molecular partition function Q is defined as sum of sum over status of an. Now if we take a single gas molecule, because here the gas molecules do not interact, then we can define the molecular partition function, which is given by small q summation over all the status exponential energy of ith state. Okay, now this is called as a molecular partition function. Okay, now the particles of an ideal gas, if you say, they could be considered that they are distinguishable if they are different from each other, and therefore a unique label could be assigned to each other. On the contrary, the indistinguishable particles are impossible to assign a unique label as they are identical to each other. That means indistinguishable particles of an ideal gas for which the partition function of a system, it can be expressed in terms of molecular partition functions and the number of particles in the system. So if they are indistinguishable, that means we can write a partition function of each molecule and then the number of the systems, as the partition function allows to calculate probability of a system occupying a state J. Such system could be assumed as isolated as a microcanonical ensemble of a particle. Okay, where the total volume, total energy and the number of particles are consistent. However, the range of energies appropriate for composition, volume and the temperature of canonical ensemble contributing to the system must be still considered for composition, volume and temperature. Now if we take write the partition function of an ideal gas of indistinguishable particles, it will be q raised power n raised divided by q factorial. Okay, so the partition function will be because they are indistinguishable, so we have to divide n factorial. Okay, so this is the partition function for an ideal. Okay, now what we will do is we will derive the canonical partition function. Okay, what is derivation of canonical partition function? Okay, there are actually multiple ways to derive the partition function. Okay, the derivation that I'm showing here is called as Janssen maximum entropy approach. Okay, now If we consider the second law of thermodynamics, okay, so according to the second law of thermodynamics, a system assumes a configuration of maximum entropy derivation of canonical partition function. Now, as I told you that the second law of thermodynamics, a system assumes a configuration of maximum entropy. Okay, so at thermodynamical equilibrium, okay, that means if it has probability distribution of rho I, that maximizes the Gibbs entropy, then entropy will be equivalent to minus kb, which is Boltzmann's constant, summation over I rho I ln of rho I, whereas I states. Okay, so this is called as an entropy. Now it is there are two constraints corresponding to this entropy of a thermodynamical equilibrium system which has maximum entropy. Okay, two constraints. The first constraint is that the probability over all the status should be equivalent to 0, sorry 1. Equivalent to 1. Then in second constraint that we have is that in canonical ensemble, the average energy is fixed because there is no exchange of energy. As a result, the average is fixed. So the average energy is given by summation over I rho I EI is given by U. So the average energy is fixed. Now if we apply variational calculus, okay, with constraints that are analogous to some sense to the method of Lagrange multipliers. Okay, we can write Lagrangian L as this will be given by minus kb summation over rho I ln of rho I, okay, plus lambda 1 minus summation over rho I plus lambda 2 summation over u minus summation over I rho I EI. Okay, now if we varying and extremizing L with respect to rho I, it leads to 0 should be equivalent to delta L because it is already at the maximum. So what we do is we'll take this equation, delta of sigma I kb rho I ln of rho I plus delta of second, that is lambda 1, minus summation over I lambda 1 rho I plus delta lambda 2 rho into summation over I okay. So what we'll take the summation out, what we are left with is delta kb rho I ln of rho I plus delta lambda 1 rho I plus delta lambda 2 rho I. Then we'll go ln of rho I delta rho I, because rho is only, that is actually constant, varying. Plus d by d rho I lambda 2 ei rho I delta rho I. Okay, so that gives us kb ln of rho I minus kb plus lambda 1 plus lambda 2 ei delta rho I. Okay, now we have derived at this equation, but this equation should hold for any variation delta rho I. Therefore it implies that rho I is given by exponential minus kb plus lambda 1 plus lambda 2 ei by kb. Okay, to obtain lambda 1, one can substitute the probability of first constraint, that means 1 is given by summation over probability of all the states should be equivalent to 1, so that is given by exponential minus kb plus lambda 1 divided by kb into z. Now here z is actually a constant number, Okay, so z here is a canonical ensemble partition function which is given by exponential lambda 2 by kb into ei. Okay, so if we isolate lambda 1 yields lambda 1 is equivalent to minus kb ln of z plus kb. Okay, now rewriting lambda 1 rho in terms of z. So what does it give us? It gives us rho I is given by 1 by z exponential lambda 2 by kb into ei. Now what we'll do is we'll rewriting s in terms of z. So it will tell us z is equivalent to s is equivalent to minus kb summation over rho I ln of rho I, that will be given by minus kb summation over rho I lambda 2 by kb ei minus ln of z, that is given by lambda 2 summation over rho I ei plus kb ln of z summation over rho I. Okay, that tell us lambda 2u plus kb ln of z. Now we have derived an equation s from this. Now what we have to do is, in order to obtain lambda 2, we differentiate s with respect to the average u and apply the first law of thermodynamics, that is delta u is equivalent to T del S minus P dV. So delta S by delta u is given by minus lambda by T. Okay, thus canonical partition function z becomes z is given by summation over I e raised power minus beta ei. Okay, so we have used the concept of the entropy in order to determine what will be the canonical partition function. Now here beta is called as a thermodynamical constant. It is given by 1 by kbt, where kb is called as Boltzmann's constant, is thermodynamic beta. Now we can also write the probability distribution rho I and entropy S as rho I will be given by 1 by z e raised to the power minus beta ei. Now this is the probability that a particular state is occupied. Okay, and S will be given by U by T plus KB ln of Z. This is the entropy. Okay. So we have determined, we have derived the equation for mechanical partition function. Now what we'll do is we'll take some systems, and from those systems we'll try to define the partition function for classical and non-classical systems, and then we will derive different thermodynamical equations from it. Okay, so first we'll take classical continuous system. So in classical mechanics, the position and the momentum variables of a particle can vary continuously. So the set of microstates is actually uncountable. There is no microstate countable state, because it is not quantized. Okay, thus the classical statistical mechanics, it is rather inaccurate to express the partition function as the sum of discrete terms. So in that case, what we must describe the partition function using an integral rather than a sum. So since there is no quantization, so number of microstates are infinite. Thus sum is replaced by integral. So Z is written as 1 by h cube. Okay, integral of e raised to power minus beta h, which is a function of q and p, d3 q d3p. Okay, where we can say that h is Planck's constant, beta is thermodynamic beta, whose value is 1 by kbt. Okay, then we have a quantity called as h, qp. This is called a Hamiltonian of the system. Okay, and q is canonical position, whereas p is canonical momentum. Okay, so this is classical continuous system. Now if we have something called as a we have classical continuous system, but they are multiple identical systems. So that time what we have to do is, for example, if we'll take a gas of n identical classical particles, we can write Z equivalent to 1 by n factorial h raised to power 3 by n h raised to power 3n, then integral over all the particles. Okay, we'll write exponential minus beta summation over I raised to power from 1 to n h qi pi, then close d3 q1 up to way to d3 qn, right? Then we have pi p1 and then d3 pn. Okay, so this is, here we have some new thing that is called as d raised power cube. It is actually a shorthand notation to indicate that qi and pi are vectors in three-dimensional space. Okay, so we have taken classical continuous system. Now here we have introduced like different things that we have shown here. For example, this n factorial that I will show you why it is taken here, and then we have an extra constant factor that is introduced in the denominator, that is this h raised power 3n. It is because unlike discrete form, the continuous form shown, that is actually I have shown here, it's not dimensionless. So in order to make it dimensionless, we have to divide it by h raised power 3n. Now we have another system. Now this consists, this was in case of a classical system. Now what we have is quantum mechanical discrete system. Now there is a quantization. So for a quantum mechanical discrete system, what we will write is that if we have a canonical system that is quantum and discrete, the partition function is defined as trace of Boltzmann factor. So z is equivalent to trace of Boltzmann factor, which is e raised to power minus beta h. Okay, so here tr is trace of matrix, beta is thermodynamic beta, which is given by 1 by kbt, and h is Hamiltonian. Operator. Okay, but if we have now this is quantum mechanical discrete system. If we have something like quantum mechanical continuous system. Okay, so in case of a quantum mechanical continuous system, here also what will happen is that we have to change the summation over the to the integral q comma p Okay, so here the q is canonical position and the p is canonical momentum. Now if we have a system with multiple quantum states s sharing same energy es, that means these states are degenerate. So when we have these states of degenerate levels, we can write partition function as so z will be equivalent to summation over I gi e raised power minus beta e I, where gi is degeneracy factor or the number of the quantum states with same energy state EJ. So this tells us the quantum mechanical and partition function for a quantum mechanical state. Okay, so now we have determined these quantities. Okay, what we'll determine is now we'll from this partition function we'll determine various parameters like various thermodynamical parameters. So the first thermodynamical parameter that we'll be calculating thermodynamic energy from partition function. Okay, now we have to see that in order to determine the different thermodynamical parameters of the total energy. So what it is actually this is expected value or ensemble. As I told you before that we create an ensemble because an ensemble creates almost all the states that are possible in a system. So this is an ensemble average for energy which is sum of microstate energies weighted by their probabilities. Okay, so E, that means the total energy E is the expectation energy that is given by this, which is given by summation over all the energies of different ensembles multiplied by their probabilities. So we'll write 1 by Z summation over S ES e raised to the power minus beta ES. So this is where probability of an S state is given by summation over S ES e raised power minus beta ES divided by Z. that we have shown before in the probability gas. So this one we are using. Okay, so let us go further. That means the expectation value of the energy will be equivalent to minus 1 by z d by d beta z, which is a function of beta, e1, e2, etc. That is given by minus d ln of z by d beta. Or we can write E expectation value is given by k b d square d ln of z by dt, whereas z is our partition function or canonical ensemble partition function. So ps here is actually for p, the probability of an acetate is not es, this. Okay, now we have determined this. Also, if we say that microstate energies, they depend on a parameter called as lambda. Okay, so es will be given by es 0 state plus lambda a s. This is true for all s, that means all states. Then expectation of value of a is asps, which is given by minus 1 by beta d by d lambda ln of z beta lambda. Okay, whereas z is the partition function. Okay, now this provides us a method of calculating the expectation value of many microscopic quantities. Okay, now what we have to do is we have to know the partition function, and then from that partition function we can calculate the expected value. Okay, now we have to see what is the relation with various thermodynamical quantities. Okay, now what we'll do is we'll do thermodynamic variables. Okay, relation with thermodynamical variables. Now we have seen that total energy E is given by minus d ln of z by d beta. Okay, that means thus variance of energy is, or the fluctuation in the energy will be delta E, right, square. Okay, that is given by E minus expectation value of E whole square, and its expectation value, that is given by d square ln of z by d beta square. Okay, so from this we can derive the heat capacity. because we know that heat capacity CV is given by d total energy by dt, which is given by 1 by kBT square expectation value of delta E square. Okay, now what is happening here is we have now should write that in general, if we consider 1 minute. Oh, it has deleted majority of the. We have seen that thermodynamical energy is given by minus d ln of z divided by d beta. Okay, so that means variance in energy, or we can say that energy fluctuations is delta E will be given by E minus will be given by d square ln of z by d beta square. Okay, therefore heat capacity is given by, that is CV will be given by d E by dt, which is given by 1 by kBT square variance of delta E square. Okay, so similarly we have now in general the extensive variable x and intensive variable y, where x and y form a pair of conjugate variables. Therefore x will be given by plus minus delta ln of z by d beta y. Now if y is fixed, then the average value of x will be given by this. Okay, so the sign will depend upon the notation of variables of x and y. Therefore delta x square, it will be given by x minus square of average will be given by d x average into d beta y, which is given by d square ln of z by d beta y. Okay, now in case of entropy, what we'll get is S will be given by minus KB summation over S PS ln of PS, which is given by KB ln of Z plus beta E, where E is called as an expectation value, which is further given by d by dt kbt ln of z, that is given by minus dA, which is called as a Helmholtz function, dA by dt. Now this is Helmholtz function. We also know that A is given by u minus ts. Okay, but here u is expectation value of E, that is total energy. Therefore A will be given by expectation of E minus ts, that is given by minus kbt ln of z. So we have derived an equation for Helmholtz function. Therefore heat capacity at constant volume can also be defined as T delta S by delta T, which is given by minus T del square A by delta T square. This is heat capacity at constant volume. Okay, now we have something called as partition function of subsystems. Okay, now this is the partition function for the whole system. If we take as partition function of subsystems. Okay, for example, if we have a system and it is broken down into n subsystems, and these subsystems do not have any interaction energy, thus we can assume that different particles, they are essentially non-interacting. Okay, so the partition function will be zeta 1, zeta 2, zeta 3. Therefore the total partition function z will be given by multiplication of all the partition functions. This is given by zeta j. This I will derive in the next session. Now, but if subsystems have same physical properties. Okay, so that means zeta 1 will be equivalent to zeta 2 will be equivalent to zeta 3 will be equivalent to zeta n. So therefore z will be equivalent to zeta raised power n. Okay, because they are the multiplication of E. But there is an exception to this rule. So exception to this rule is this, that if subsystems are identical, these are those where the subsystems are not identical but they have the same partition functions. But if the subsystems are identical, then in quantum mechanical sense, it is impossible to distinguish even in principle. So these subparticles, these subsystems, they cannot be distinguishable. Thus total partition function, thus the partition function has to be divided by n factorial. So total z will be equivalent to zeta raised power n divided by n factorial. This is for uh, uh, subsystems that are indistinguishable. Okay, so now this is because we should not count the microstates, and this is called as Gibbs paradox. The factorial n factorial is divided so that we should not count the subsystems, and this property is called as Gibbs paradox. Okay, now what is the meaning of all this? No, it is not it might not be obvious that the partition function as we have defined it is an important quantity, but for example, if we consider the partition function is a function of temperature and different microstate energy like E1, E2, E3, E4. The microstates are actually determined by other thermodynamic parameters and the number of particles and the volume as well as the microscopic quantities, just like the constant particles. This dependence on microstate variables is the actual point of statistical mechanics. Okay, with the model of microscopic constituents of a system, one can calculate the microstate energies and thus the partition function, which will then allow us to calculate all other thermodynamical properties of a system. The partition function of can be related to thermodynamical properties because it is very important statistical meaning. The probability of a system occupying microstate S is given by, for example, the probability of a system occupying microstate S is PS will be given by 1 by Z e raised to the power minus beta ES. So this is the probability. Thus partition function plays a very important role in normalizing the probability. It ensures that the summation over all the probabilities of all the states will be equivalent to 1. How? We write 1 by Z summation over e raised power minus beta S. This is summation over S. So therefore it will be Z 1 by Z, that is given by 1. Okay, thus partition function is directly related to the probability, and it encodes how the probabilities are partitioned among different microstates based upon the individual energies. Other partition functions for different ensembles, they divide up the probabilities based on other microstates. As an example, the partition function of a isothermal isobaric ensemble, the generalized Boltzmann distribution, it divides up the probabilities based on particle number, pressure, and the temperature. Similarly, the energy is replaced by characteristic potential of that ensemble, the Gibbs free energy. The letter Z stands for the word Zustand Sumi. Okay, so this is actually a German word. Okay, it means some over states. Okay, the usefulness of the partition function, it stems from the fact that microscopic thermodynamical quantities of a system, they can be related to the microscopic details through the derivation of the partition function. Finding a partition function is also equivalent to performing a Laplace transform of the density of the states function from the energy domain to the beta domain, and the inverse Laplace transform of the partition function reclaims the energy density of the samples. Okay, now we have something called as a grand canonical partition function, and we have something called as a okay, so grand canonical I will finish this today. Then on the next session we can go to we call it as molecular partition function. Okay, so now we have something else called as grand canonical partition function. So grand canonical partition function is for a grand canonical ensemble. It describes a statistics of constant volume. It can exchange both heat and particles with reservoir. So it has only the constant volume, but it has constant temperature and it has constant potential. Thus it can exchange both heat and particles with that of the reservoir. This constitutes the grand canonical partition function. Okay, thus it has constant temperature, it has constant chemical potential. So mu is chemical potential. Now the grand canonical partition function, which is denoted by z. Okay, so it is denoted by z cross. Okay, is following sum over microstates. Okay, so it is minus kbt ln of z cross, which is given by okay, so it is all over this states. Okay, so canonical partition function is z, which is given at constant potential, constant volume and constant temperature. It is summation over all the status exponential ni mu minus e by kbt. Okay, here I constitutes a particular state and n is the ni is the I microstate has ni particles and energy ei, that is distributed among ei particles. Therefore the partition function is also related to grand potential in, so grand potential is phi g, which is given by minus kbt ln of z is given by grand potential, g is given by e minus ts minus mu n. Okay, this is in contrast to the canonical partition function, which is related to related instead of Helmholtz free energy. Now this is very important. This is very important to note that the number of microstates in a grand canonical ensemble may be much larger than that of canonical ensemble. Because here we consider not only the variation in the energy, but also we consider the variation in the particle number. Again, the utility of grand canonical partition function is that it is related to probability that the system is in the state I. Okay, therefore the probability pi will be given by 1 by z grand canonical partial function exponential ni mu minus ei by kbt. Okay, now an important application of the grand canonical ensemble is in deriving exactly the statistics of non-interacting many-body quantum gas like Fermi-Dirac gas for fermions, Bose-Einstein statistics for bosons. However, it is much more generally applicable than that. The grand canonical ensemble may also be used to describe classical systems or even interacting quantum gases. The grand canonical partition function is sometimes written in terms of alternate variables, as it can also be written as z as a function of zvt is given by summation over ni z raised power ni. Okay, then z ni v and t, where z is exponential mu by kb t. This is known as absolute activity or fugacity. Now in chemical kinetics you might have heard about fugacity. The fugacity comes from this, and z n v t is the canonical partition function. Okay, so what we have done is that we have put this into from grand canonical partition function into the canonical partition function as well. Now this completes our today. In the next session we'll be dealing with the molecular partition functions, how the different partition functions are can be correlated for a single molecule, okay, in terms of its different states of matter. Now, for example, so today what I briefly discussed today, what we have explained here is I have given a brief introduction about the statistical thermodynamics. What are the different uh, types of canonical ensembles? Okay, so first I have taught about the probability in the previous lectures. Then we have taught about the distribution, then distribution functions. Then what are the different types of bosons, fermions, and the bosons, permutations and combinations, and energy distribution of different particles. Today first I have told you what is the importance of Stirling's approximation in quantum mechanics, and what is then also I have told you about for fermions and bosons, what are the different types of fermions, and what are the different types of fermions and the bosons. Okay, so the fermions should have an asymmetrical wave function. Okay, that asymmetrical wave function, it can be derived using the Slater determinant functions. Okay, then we have I have explained about how for fermions how we can devise the symmetric and antisymmetric wave functions. But for the bosons it's not the case. So in case of the bosons it should be symmetric. Okay, then I have told about the Fermi Dirac distribution function that is applicable in case of fermions. So if we from the Fermi Dirac distribution comes the concept of Fermi level. So if we have, for example, at T is equal to 0 Kelvin, we have the Fermi function is equivalent to 1 when it is greater than once when the energy is less than the Fermi level. But once the energy is higher than the Fermi level, then what happens is that none of the energy states is occupied. Okay, so this Fermi level is defined in case of the gases, because at high temperatures what will happen is that those states which are near to the Fermi level, they are taken from those states, and higher energy states are occupied in the E. Then I have derived the concept of the partition function. Okay, what the partition function is telling us that uh, different types of the partition functions and how it is correlated with different types of the. Then I have derived the partition function for an ideal gas, for a canonical ensemble partition function. From the canonical ensemble partition function we have derived how it is related to different thermodynamical quantities like entropy A. And then I have derived what is the grand canonical partition function, or the partition function of the subsystem. So in the next what we'll define is we'll tell about what are the different functions. In the next we'll tell about the in the next session there will be a discussion on the molecular partition functions and how we can derive different molecular partition function equations. Thank you.